Today I'm answering this IGCSE Edexcel 1C paper and it's from May 2020. There's the periodic table. Question 1. This question is about chemical elements. Use the periodic table to help you answer this question. Identify the element with atomic number 5. So double check the key. We're looking for the bottom number. We need to look for the one which is number 5. So that's boron. To give the symbol of a metallic element in period 3. So let's count down the periods. Here's period 1, here's period 2, here's period 3. We need to look at the left hand side of the periodic table, so we could either pick sodium or magnesium. Aluminium would also have been fine. Identify the element whose atom contain 14 protons. Well, protons is the same as the atomic number, so we're looking for an element with an atomic number of 14. That's silicon. Identify the element whose atoms have the electronic configuration 2,5. So that means you want an element in period 2 because it has 2 electron shells and 5 electrons in the outer shell. So we're zooming in on group 5. Period 2, which means it's nitrogen. Give the name of the compound formed between oxygen and the element with atomic number 13. So atomic number 13 means it's aluminium. So we need a compound with both aluminium and oxygen in the name. So remember, the metal always comes first. We change the ending of the word oxygen to aluminium oxide. The position of an element in the periodic table can be used to predict its properties. Which group contains elements that are all unreactive? Well, you want the group that has a full outer shell, which is group 0. Which of these is the least reactive element in group 1? So, focusing in on group 1, the least reactive can be found at the top of the group. So, lithium hopefully is in the suggestions. Yes, it is. 2. The boxes list changes that may happen in a laboratory and the names of some changes. Draw one straight line from each of the change to its correct name. Ice turns into water. This is melting. Solid carbon dioxide turns directly into a gas. So we're going straight from a solid to a gas with no liquid intermediate, which is sublimation. A solute is stirred into a solvent. That is our definition of dissolving. A student has 2 solids, X and Y. One of these solids is a pure substance, the other one is a mixture. Describe how the student could identify which solid is pure and which is a mixture by measuring a physical property of each solid. The clue here is the physical property. It means you need to measure something like its boiling point or melting point. If something's pure, it boils or melts indeed at the same temperature. If it's a mixture, it will show a range of boiling points. So test both substances' boiling points. If the boiling point is fixed, substance is pure. If the boiling point occurs over a range of temperatures, the substance is a mixture. Question 3. This question is about metals. Metals can be arranged in a reactivity series based on their reactions with water and their reactions with dilute hydrochloric acid. The table shows how 4 metals, P, Q, R and S, react with water and with dilute hydrochloric acid. Identify which of the metals P, Q, R or S could be gold. Gold is very unreactive, so we need one with no reaction with either water or hydrochloric acid. So that's Q. Suggest why the reaction between metal R and dilute hydrochloric acid was not done. It must be because it's really dangerous, so it must be a very reactive metal. R is very reactive, so a reaction with the hydrochloric acid would be too dangerous. Use the information in the table to place the metals in order of reactivity from most reactive to least reactive. So I'm going to number them 1 to 4, 4 being the least reactive, 1 being the most. So the fact that R wasn't done because it was too dangerous means it must be the most reactive. Then we need to look at the hydrogen gas forming. If it's formed more quickly, it must be pretty reactive, followed by forming slowly and then not at all. So we go RS, PQ. Zinc is used to coat iron gates to prevent the iron from rusting. State the name of this method of preventing iron from rusting. This is known as galvanizing. State another method of preventing iron from rusting, well, as simply as using grease or oil or painting, because it's a barrier method. A mixture of zinc powder and copper 2 oxide is heated. The chemical equation for this reaction that takes place is. State how the reaction shows that zinc is more reactive than copper. Well, we can see that the zinc has displaced the copper from the copper oxide. Explain which substance is the oxidizing agent. So by definition, an oxidizing agent causes another substance to gain oxygen. So the substance gaining oxygen is the zinc. So what's causing that? Well, it must be the copper oxide. Question 4. Sodium hydroxide dissolves in water, forming a strongly alkaline solution. Ammonia dissolves in water, forming a slightly less alkaline solution. Identify the ion that makes the sodium hydroxide solution alkaline. So remember, H plus ions form acids, OH minus are responsible for alkalines. You could also write hydroxide. What is the possible pH for ammonia solution? So remember, between pH 8 and 14 is alkaline, which means we need to pick between these two numbers. 14 is very strong. We've just been told that it's not super alkaline, so it must be 11. When ammonia solution reacts with sulfuric acid, a neutralization reaction occurs and ammonium sulfate forms. How does the sulfuric acid act in this reaction? So we've got ammonia reacting with sulfuric acid to form ammonium sulfate. So what does the sulfuric acid do? Well, it donates the H+, which remember is a proton, so it's a proton donor. The diagram shows a beaker containing some ammonia solution and a few drops of phenolphthalein indicator. Dilute sulfuric acid is added to the beaker until it is in excess. What are the colours of phenolphthalein indicator before and adding the excess sulfuric acid? So we're going from alkaline to acidic. So you do need to learn the colour of your indicators. Remember, the phenolphthalein is the beautiful one that's colourless or pink, which means we're zooming in on these two options. C is the correct answer. It's pink in alkali and colourless in acids. Ammonium sulfate is used by gardeners as a fertiliser because it contains nitrogen. Explain why the chemical formula of ammonium sulfate is NH42SO4. Refer to the charges on the ions in your answer. Oops, I literally just did that equation higher up. So let's point out that we have an NH4 plus ion and SO42 minus. Therefore, 2 NH4 plus ions are needed for each sulfate ion in order for the charges to balance. Calculate the relative formula mass of ammonium sulfate. So remember, you need to use your periodic table for this to find the relative atomic masses. So nitrogen is 14. We need to times it by 2 because of that 2 there. In terms of our hydrogens, we've got 4 within the bracket, but again multiply it by 2, so we need to do 8 lots of 1 plus sulfur, which is 32, plus 4 lots of oxygen, which is 16, to get 132 as our answer. Calculate the mass in grams of nitrogen in 1 kilogram of ammonium sulfate. So we need to find out what percentage of that compound is made up of nitrogen. So from here we can see that there are 2 lots of nitrogens, which is why we're doing that. So let's do that calculation. First of all, we times it by 100 to work out the percent that's made up of nitrogen. So from the periodic table, we do 2 lots of nitrogen, which is 28, over the MR that we've just calculated, So we know that of the compound, 21.2% of it is nitrogen. So let's do 21.2% of that kilo. Let's convert it to grams because that's what the question asked for, to get an answer of 212 grams. Chlorine, bromine and iodine are elements in the periodic table. Explain how the position of these elements in the periodic table depends on their electronic configurations. Well, we can see that they're all halogens, they're all in group 7, and that's because they all have 7 electrons in their outer shell. Chlorine reacts with methane to form CH3Cl and HCl. State the condition necessary for this reaction. Well, that's UV light. Give the equation for this reaction. So chlorine is diatomic, so it's made up of 2 atoms. Methane has the formula CH4, and we know what we're forming because they've provided that kindly in the question. The bonds in a molecule of CH3Cl are covalent. Explain in terms of electrostatic attractions what is meant by a covalent bond, so you need to define this fully. This is the electrostatic force of attraction between a shared pair of electrons between the nuclei of 2 atoms. Draw a dot and cross diagram for the molecule of CH3Cl showing the outer electrons on the atoms. So carbon is in group 4, so it has 4 electrons in its outer shell. Hydrogen has 1 electron in its outer shell. Chlorine has 7. Remember to use the periodic table to help you with this. Let's start by drawing our circles to represent the outer shells. So I'm going to start by drawing those 4 electrons on the carbon. 1, 2, 3, 4. Then remember hydrogen has 1 electron in its outer shell here. Chlorine has 7. 1, 2, 3, 4, 5, 6, 7. Let's sit back and see if we've got full outer shells everywhere. 2, 4, 6, 8. Yep, carbon's happy, it's got 8 electrons. 2, 4, 6, 8. Yes, chlorine's happy, it's got 8 electrons. Remember, hydrogen only has 1 shell of electrons, and the first shell can contain a maximum of 2 electrons, which is why that's correct. CH3Cl has a simple molecular structure. Explain why CH3Cl has a low boiling point. So they've told us it's a simple molecular structure, which means by definition it has weak intermolecular forces, which remember require little energy to break. Graphite is another substance that contains covalent bonds. The diagram shows the structure of graphite. Most covalent substances do not conduct electricity. Explain why graphite is able to conduct electricity. That's because graphite has 1 electron per carbon atom, which is delocalized and therefore free to move. Question 6. The table shows the molecular formula of 6 organic compounds, A, B, C, D, E and F. Explain which homologous series compound B belongs to. Let's draw it quickly. So remember, each carbon atom forms 4 bonds, each hydrogen atom forms 1 bond. So this is how you draw C2H6. Now we can see by looking at it that it's an alkane. What do we know about alkanes? Well, they obey the general formula CnH2n plus 2. So B obeys the general formula CnH2n plus 2. Give the letter of the compound that has the same empirical formula as its molecular formula. So remember, the empirical formula is the simplest ratio of atoms of each element. The molecular formula is the actual number of atoms of each element. Just going to change colour, give myself some space. So these are the molecular formulae. Underneath I'm going to cancel them down if I can, and that would be the empirical formula. So C2H4 is the same as CH2. C2H6 becomes CH3. I'm just cancelling them down. CH2. That doesn't change. CH2. C2H5. So because it hasn't changed, it means the empirical formula must be the same as the molecular formula. So the answer here is D. Compound F exists as 2 isomers. Explain what is meant by the term isomer. Include the structures of 2 isomers of compound F in your answer. So an isomer has the same molecular formula but different displayed formula. compound F is C4H10. So let's get drawing. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Amazing. Fill up with hydrogens. To form an isomer, let's just shorten that carbon chain to just 3 and have an individual mini branch coming off. Remember, each carbon atom forms 4 bonds, each hydrogen forms 1 bond, which is why I'm drawing it this way. And I want to count up to make sure I've got C4H10. Count the hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. Remember, we can't draw that carbon off here or here because it just turns into this isomer again. Describe how compound D can be obtained from crude oil using the industrial process of fractional distillation. So compound D is C3H8. So remember, we have to heat the crude oil until it vaporizes. Then you pass that vapour into the bottom of the fractionating column. And remember, fractional distillation basically relies upon the fact that the crude oil contains fractions with different boiling points, so they condense at different positions within the fractionating column. So fractions condense at different positions within the fractionating column because they have different boiling points. And have a look. We've been asked about compound D, so refer back C3H8. D will condense towards the top of the fractionating column. Why? Because it's a shorter chain, so we'll have a lower boiling point. Compound C can be used to make a polymer. State the type of polymer formed from compound C. Okay, so that's an alkene. So remember, we're really talking about addition polymerization here. Name the polymer formed from compound C. So which alkene was it? C3H6. So C3H6, remember, is propene. So it must be polypropene because to turn it into a plastic, remember, we add poly to the front of its name. Draw the structure of this polymer, include the displayed formula of the repeat unit. Here's our propene, which remember is unsaturated, so it has that double bond. We need to break that double bond and redraw it. Elongate those bonds and then show that we've got several subunits. Dilute hydrochloric acid reacts with a solution of sodium thiosulfate to form a precipitate. The equation of the reaction is this. State the name of the precipitate that forms. So we need a solid because we're talking about precipitates, so it's just sulfur. Don't get over stressed by that question. The reaction is often used to investigate rates of reaction. The diagram shows the apparatus the student uses to investigate the effect of temperature on the rate of reaction. This is the student's method. Pour 50 centimetres cubed of cold sodium thiosulfate solution into a conical flask and heat to 20 degrees Celsius. Draw a cross on a piece of paper and place it under the flask. Add 5 centimetres cubed of dilute hydrochloric acid to the flask. Look at the cross from above and record the time taken until the cross cannot be seen. The student repeats the experiment 4 times using sodium thiosulfate solution at different temperatures each time. He keeps the volumes of sodium thiosulfate solution and hydrochloric acid constant. Give 2 other factors that the student should keep constant. Okay, well, it's concentration because after all we're changing the temperature. So it's concentration of the sodium thiosulfate solution as well as the concentration of hydrochloric acid. The table shows the student's results. The highest temperature the student uses is 60 degrees because he thinks the results might not be as accurate as temperatures higher than 60 degrees. Suggest a reason why the results might not be as accurate at temperatures higher than 60 degrees. Well, if the temperature is too high, then we'd have too short a time reading, which would mean that it was more likely to be inaccurate. So if the temperature was too high, the cross would disappear too quickly, leading to less accurate time readings. The student wants to compare the rates of reaction at different temperatures. He uses the formula to obtain a value for each rate of reaction. The table shows the value of the rate of reaction at each temperature. Plot the values of temperature and rate of reaction. Draw a curve of best fit. So at temperature 20 degrees, we've got a rate of reaction which is 0.0025. That's down here. At 30 degrees, we've got 0.0053. At 40 degrees, 0.012. 50 degrees, 0.023. And at 60 degrees, 0.042. Here's our curve of best fit. Use the graph to determine a value for the rate of reaction at 45 degrees and show on the graph how you obtained your answer. So we do need to draw this line. Here's 45 degrees. Take that line up and then read across. So if that's 0.015, we're just a bit higher than that. So 0.0162 is the value I'm going for. Calculate the time that it would take for the cross not to be seen at 45 degrees. So we're using the equation rate equals 1 over time. We've just found the rate from the graph, so we're looking for t. So you want to cross multiply, so that means doing 1 divided by 0.0162. So that comes out at 61.7. Remember, these readings will vary slightly depending on your own graph. Describe the relationship between rate of reaction and temperature shown by the graph. Nice simple description. As temperature increases, rates of reaction increase. Explain in terms of particle collision theory the effect that increase in temperature has on the rates of reaction. Okay, nice straightforward recall question here. So as temperature increases, kinetic energy of particles increases. Write that out in full. There is more successful collisions per unit time, so rate of reaction increases. A student uses this apparatus to investigate the heat energy change when a salt dissolves in water to form a solution. This is the student's method. Add 50 centimetres cubed of distilled water to a polystyrene cup, record the initial temperature, add a known mass of solid anhydrous copper 2 sulfate to the cup and stir the solution with the thermometer until the solid has dissolved. Record the maximum temperature of the copper 2 sulfate solution. Name the piece of apparatus the student should use to add the distilled water to the polystyrene cup. A pipette would be fine here. You could also say burette or measuring cylinder. The student stirs the solution to help the solid dissolve more quickly. Suggest another reason why the student stirs the solution. Well, that's to ensure that the temperature is the same throughout the solution. State the colour of the copper 2 sulfate solution. Oh wow, that's quite an interesting one. Remember, it's that beautiful turquoise blue colour. The diagram shows the temperatures in one experiment. Complete the table giving all values to the nearest 0.1 degrees Celsius. Maximum temperature in degrees Celsius. So that's 25, 26, 27.3. Initial temperature, now looking at this side, 21, 22, 23, 24.4. So the increase in temperature is the difference between those two numbers, which is 2.9. In a second experiment, when a student dissolves the anhydrous copper 2 sulfate in 50 centimetres cubed of distilled water, the increase in temperature is 3.3 degrees Celsius. Show that the heat energy change in the second experiment is approximately 700 joules. So people love subbing the answer into their working. No. You're going to do your working and then double check and hopefully see that your answers are about the same. So the heat energy change, you need this equation, Q equals mc delta T. So after Q, we know that 1 centimetre cubed of water has a mass of 1 gram. We've got 50 centimetres cubed, so that's why it's 50 grams, times the specific heat capacity we've been given, times that temperature change, which is 3.3. Pop that into your calculator to get 693 joules. Well, thank goodness, that's around 700 joules, so we're all good. In this experiment, the student uses 1.7 grams of anhydrous copper 2 sulfate. Calculate the molar enthalpy change, delta H in kJ per mole. Include a sign in your answer. We're after delta H. Notice the units. Well, it's energy, because it's kilojoules, and then it's moles. The formula we need is energy divided by number of moles. So we know the energy, because we've just calculated it, is 693. Remember, that needs dividing by 1,000 to get it into kilojoules. And then obviously we need to find the number of moles. We're going to use this formula triangle. So we can see that number of moles is mass divided by MR. So we've been told that the mass of anhydrous copper sulfate is 1.7. The MR we've been told here is 159.5. Don't round that number. So that's our number of moles, so we can pop that here and then just finish off that calculation to get 65.0. And we need a sign in our answer. So we know it's an increase in temperature, which means it's an exothermic reaction. So we need a negative sign here. Another student does a similar experiment but uses hydrated copper 2 sulfate instead of anhydrous copper 2 sulfate. The table shows his results. Explain what the results show about the type of energy change that occurs when hydrated copper 2 sulfate dissolves. So we can see that the temperature has decreased, which means it must be an endothermic reaction. Sodium hydrogen carbonate is also known as baking soda. Baking soda can be used to make cakes increase in size in an oven. This is the equation for the reaction that takes place when baking soda is heated. What type of reaction is this? So that's breaking down into its different components, which means it's thermal decomposition, particularly because we know it's been heated. Heated thermal, breaking down, decomposition. So B. Suggests why the reaction makes the cakes increase in size. Well, let's look at our products. We're producing carbon dioxide gas, and those gas bubbles will therefore make the cake increase in size. A student uses this apparatus to investigate the reaction that takes place when sodium hydrogen carbonate is heated. This is the student's method. Weigh a crucible and record the mass. Add some sodium hydrogen carbonate to the crucible. Reweigh, record the mass. Heat the crucible and contents for 5 minutes. Allow to cool before weighing and recording the mass. Heat the crucible and contents again for further 3 minutes, then allow to cool before weighing and recording the mass. Give a reason why the crucible and contents are heated for a further 3 minutes. The reason why you keep heating and cooling is to obtain a constant mass so you can prove that the reaction is complete. The student considered using a lid on the crucible in the experiment. Suggests an advantage and disadvantage of using a lid on the crucible. Well, an advantage would be to stop any of that sodium hydrogen carbonate spitting out. However, disadvantage is it would mean that the carbon dioxide and water which is escaping wouldn't be able to leave as easily. The table shows some of the students' results. Calculate the mass of sodium hydrogen carbonate that the student uses. 29.75 minus 26.50 equals 3.25 grams. Using this equation, calculate the maximum mass of sodium carbonate, Na2CO3, that could form in the student's reaction. So let's write out that equation below so we can access it more easily. We're going to use the table format that states mass, MR, and number of moles on the left-hand side. Here's your all-important formula triangle. So we're after the maximum mass of sodium carbonate, which is why this is X. We know that our mass of sodium hydrogen carbonate is 3.25 because we've just found that out. Let's pop our MRs in this table, which we've been kindly told is 84 and 106. Then using this formula triangle, we can see that number of moles is mass divided by MR. So let's do that for sodium hydrogen carbonate first of all. So that's 3.25 divided by 84 to get this long number. Then check the mole connection. It's 2 to 1, which means we need to divide that number by 2 to find the number of moles of sodium carbonate. And then finally, to find that X, that mass, we do MR times number of moles. So we do 0.01934 times 106 to get 2.05 grams. In a second experiment, the student uses a larger mass of sodium hydrogen carbonate. She calculates that she should obtain 4.8 grams of sodium carbonate. She actually obtains 4.2, calculate the percentage yield. So to do that, you need to do the actual mass divided by theoretical mass times by 100. So she actually obtains 4.2, she ought to have obtained 4.8, and that's 87.5%. Other than spillages suggests a possible reason why the student's actual yield is less than expected. Well, that's going to be due to the purity of that original sodium hydrogen carbonate. The table gives information about some lead compounds. When a sample of red lead oxide is heated, it changes into a yellow solid and a gas forms that relights a glowing splint. Complete the word equation for this reaction. So we know from the gas relighting and glowing splint that we must have oxygen. We know that we're forming a yellow solid, so that means that the other substance is lead 2 oxide. A sample of one of the oxides of lead contains 86.6% lead, 13.4% oxygen by mass. Show by calculation that the sample is lead 4 oxide PbO2. So we're doing an empirical formulae calculation. So again, we're using a table. So we start by listing our elements. So that's lead and oxygen. What are their masses? Well, you're allowed to just take their percentages because they're proportional. Then we want their relative atomic mass. I'm just going to write MR here. We know that that's 207 and 16. So to find the number of moles, we do mass divided by MR. 0.4183. 13.4 divided by 16. 0.8375. Now you want to divide by the smallest number. 0.41. Divide both by that. And you'll get a ratio of 1 to 2. PbO2. Which, guess what, is what they told us it would be in the question, so we know we've definitely got it right. Red lead oxide reacts with warm dilute nitric acid. Complete the chemical equation for this reaction. So because this looks quite complicated, this balancing, I'm going to use the proper method for doing this. So I'm listing my elements on both sides of the equation. Now we're using a tally chart. So how many leads do we have on the left-hand side? That's 3. Oxygens is 4, and then 4 lots of 3 there, so that's 12 plus 4, which is 16. Hydrogens is 4, and nitrogens is 4. Let's sort it out on the right hand side. So we've got 2 leads, 6 oxygen, 8, 9. Hydrogens we've got 2, nitrogens we've got 2. So let's start by trying to sort out our leads. I'm going to put a big 2 here and see what adjustment that makes. So now we've got 1, 2, 3 leads here. In terms of nitrogens, we've got 2 times 2, so that's 4. Oxygen, we've got 6 here times 2, which is 12, 14, 15. So let's sit back and see if we've got any further issues. Yeah, we don't have enough hydrogens on the right hand side, so let's put a 2 here. So that now becomes 4. Double check our oxygens. We've got 6 times 2, 12, 14, 16. And then sit back. Are they balanced? Yes, they are. We just need to add state symbols now. So we know that the lead oxide is solid. The nitric acid, as with all acids, is aqueous. And that's us done. A student is given a sample of solid red lead oxide and some dilute nitric acid. Describe how the student could obtain a pure sample of lead to nitrate crystals. Okay, this is a making salt answer. 6 marks though. Wow. The first point we want to make is to warm the nitric acid and add it to the lead oxide. Filter to obtain lead 2 nitrate solution. Heat the solution to evaporate some of the water. Leave the solution to cool. Filter the crystals and dry using a warming oven.